Presented by AmazingPhysicsForAll.com. No doubt, soap bubble amazes everyone, and it is always a fun playing with it. You dip a small ring in the soap water, and then gently blow air through the ring. There comes, like a magic, a perfectly spherical soap bubble. As it drifts in the air, it starts displaying spectacular colors. Have you ever wondered what makes a soap bubble so colorful? What is the physics behind this? What phenomenon paints a soap bubble with such beautiful colors? To comprehend how a soap bubble gets so colorful, we need to first understand a few basic concepts related to wave nature, such as wavelength, phase of a wave, crest, and trough. Also, we need to find out what happens when two waves meet at a point and interfere with each other. Consider a typical wave as the figure shows. The points where the wave has the highest amplitude are crests, where it has the lowest amplitude are troughs. The distance between two successive crests or two successive troughs is the wavelength of the wave. The phase of the wave indicates what point the wave is at a particular time. Now let us see what happens when two such waves meet at a point. When two waves meet at a point, the outcome of the merger depends on what phase each wave is. For example, the figure shows two waves, A and B, which are out of phase by 180 degrees. It means that when the wave A is at the crest phase, wave B is at the trough phase. So, when these two waves meet at a point, they cancel, destroy, each other. This is known as destructive interference of waves. Now let us see what constructive interference is. Take a look at this figure shown. Here, the two waves are fully in phase with each other all the time. That means, while the wave A is at the crest phase, the wave B also happens to be at the crest phase. While the wave A is at trough phase, wave B is also at trough phase. When such waves meet at a point, they amplify each other, and the resultant wave will have double the amplitude at any point of time. This is known as the constructive interference of waves. Now we know what constructive and destructive interference of waves are. Let us get back to the soap bubble. It is obvious that the white light that falls on the bubble does something magical to produce this colorful effect. What is that magic? We know that light is also a wave. James Maxwell showed that it is an electromagnetic wave. The wave nature of light is responsible for many amazing phenomena. Interference of light is one of them. Interference of light is the phenomenon that makes the soap bubble so colorful. Like any mechanical wave, light waves too can undergo interference in certain situations. One of the situations is when light encounters a thin film such as the wall of a soap bubble. Let us investigate what is going on in a soap bubble. The wall of a soap bubble consists of extremely thin layer of water sandwiched between thin layers of soap. The thickness of the wall is in the order of micrometers, 1/1,000,000 of a meter. In addition, the thickness is not uniform. Consider a ray of sunlight falling on the surface of a soap bubble. When a ray of sunlight, incident ray, falls on the soap bubble, at point A, part of it gets reflected from the top surface and becomes R1. And the rest enters the thin layer and gets refracted. Remember, white light is made of many visible colors with different wavelengths. So, from point A to B, each color takes a different path. And when it reaches the inner surface, point B, part of the light exits the second surface and part of it gets reflected, internally, back to point A, as the figure shows. That reflected ray, from point B, gets refracted again at point A and exits the outer surface to become R2. When two such reflected rays, R1 from the outer surface and R2 from the inner surface, meet at point A, they interfere with each other. This interference of two or more light rays creates the spectacular colors on the surface of a soap bubble. The phase of R2 depends on the thickness of the wall and also on the wavelength of the light color. So, when R1 and R2 meet at point A, which could result in either destructive interference, that point will appear dark, if R1 and R2 are out of phase by 180 degrees. Or constructive interference, that color gets enhanced, if R1 and R2 are in phase. Or partial destructive or constructive interference, if the phases of R1 and R2 are between 0 and 180 degrees. This results in the color being less bright and seeing a mixture of multiple colors. Since the interference of these two reflected rays could be either destructive or constructive, or partially constructive, the result could be either darkness or an amplified color, or combination colors, respectively. In addition, the thickness of the bubble's wall is not uniform. So, there could be various degrees of constructive interference of colors at different points, causing a wide variety of colors. To conclude, the spectacular colors that we see on a soap bubble are the result of interference of two sets of reflected light rays, one reflected from the outer surface and the other reflected from the inner surface of the wall of a soap bubble. If you would like to read more on similar topics, please visit amazingphysicsforall.com. Thanks for watching.